Hi, Jake.
Hi, good afternoon to you. How are you doing?
Yeah, afternoon. How are you?
Yeah, good, thanks.
Do you want to check if you can share your screen? I just made you a co-host. So.
Yep, good idea. I'll try that now. Also check that the camera is working. Hopefully you can see me.
Yeah, I can see you. Sorry, I'll turn my camera on. Right.
Okay.
Oh, yeah, look
good. Yeah.
Yeah, yeah.
Okay. Great.
I was gonna let Kanishk go first, but I can't see him.
Yeah.
So.
No problem. Well, I'll stop sharing my screen for now. And then,
Yeah. Cool.
Yeah, we'll see how it goes.
So just to clarify, the turnout varies quite a bit, but we do end up putting them online. So yeah, people watch them online. So.
Yeah. No
it won't only be for 5 people.
That's fine.
Hey Kanishk, do you mind trying sharing your screen just to see if it works?
Yeah, just a moment. Can you see the screen?
Yep.
I can
Yeah,
try
yeah.
the slideshow as well just to see if things are fine.
Looks good to me.
Still fine?
Yeah, all good.
Okay.
You can keep sharing, it's fine. We'll wait a few more minutes and then I'll introduce you and we'll start the talks.
Sounds good.
Yeah. I was saying to Jake, we do record them and put them online, so the turnout kind of varies between each month, but So it won't be like other people watch the talk online usually. So
That sounds fun.
yeah. We'll wait for 2 more minutes and then get going.
Sounds good.
Okay, Kanishk, are you ready?
Yeah.
Yeah, cool. So I'll introduce you first and then we can get going. So welcome everyone to the 21st set of talks on climate interventions. So our first speaker is Dr. Kanishk Gohil from NCAR in the US, and he will be speaking about warm cloud microphysics, the climate impacts and implications for marine cloud brightening. So Kanishk, go ahead.
All right. Thanks for the introduction, Matthew. Hi, everyone. I am delighted to be invited to give a talk at the Climate Intervention Virtual Symposium number 21. I would first like to quickly acknowledge the Quadrature Climate Foundation, who fund the project that my work is a part of. And as already mentioned, I'll be talking about warm cloud microphysics and some of the work I've been doing over the past few months that could be relevant for climate intervention, specifically via marine cloud brightening. And just as like a full disclosure about my talk, it's going to be a little bit less about marine cloud brightening and more about aerosol cloud interactions, particularly pertaining to warm cloud microphysical processes. And with that, let's just get into it. Uh, all right. So climate intervention, otherwise known as geoengineering, is basically a large-scale manipulation of the Earth's climate system to counteract the effects of anthropogenic climate change. And there are several proposed methods to do so, as highlighted in this really nice figure, which I picked up from NOAA. And one of those methods is marine cloud brightening, or MCB for short. Now, MCB is typically deployed in the lower free tropospheric regions, which basically involves spraying aerosols like sea salt, sulfate, or essentially like cloud active aerosols over marine environments to basically trigger brightening of clouds in these regions, basically with the aim of reflecting some of the incoming shortwave radiations and thereafter cooling the Earth. In essence, MCB is tied closely to the aerosol cloud interaction processes, or ACI for short, which is also known as, which is also like identified as the most uncertain component of the net aerosol effective radiative forcing estimates that we get from our climate models. And so, uncertainties in ACI would essentially need to be addressed if we want to use these models for making credible MCB recommendations in the future. Now, the ACI that are particularly important in context of MCB involve warm cloud microphysical processes. Basically, what happens is that we have these aerosols in the atmosphere called cloud condensation nuclei, or CCN. And when the relative humidity in the prescribed or provided meteorological conditions exceed 100%, these CCNs swell up by taking the excess water to form cloud droplets. And then these droplets come together to form clouds. Since the underlying aerosol affect the climate and the atmosphere indirectly, via forming clouds. This is also known as the indirect effect of aerosols, which can be of two types. The first type is the first indirect effect, or the Toomey effect, that relates to the radiative forcing of the clouds. And the second indirect effect is the Albrecht effect, which relates to precipitation, cloud lifetime, and some of the other physical properties of the clouds. Since this work is mainly related to marine cloud brightening, the focus is going to be on the Toomey effect. And as for the challenges associated in this work, the CCN activation is basically thought to be at the heart of it all. Um, and the reason why CCN activation is considered to be such a problem is because it has been shown to be the case for the last several years. For instance, here is a table which I present from a paper that was published in 2014 that studied the application of different CCN activation mechanisms in CESM1, or rather CAM5. And they found large negative biases in almost all of the cloud microphysical and radiative properties. They also found that some of these biases in, let's say, the droplet number counts, the cloud optical thickness, as well as the liquid amount could be reduced simply by implementing different activation methods. Now, in CESM2, the cloud microphysics underwent several changes, but not much was done to sort of modify the underlying aerosol cloud processes. And so these biases are kind of still present, such as those within the shortwave cloud forcing. Excuse me. Here I show a plot from Gukhan Danapasoglu's paper in 2020. That was basically the review of CESM2. On the left, we have the shortwave cloud forcing component from the series EBAF product. And on the right, we have the difference between the shortwave cloud forcing simulated from CESM2 compared to the observations. And we clearly see that these biases and errors have not really gone anywhere. And these types of biases, specifically in context of warm clouds, may be tied very closely to CCN processes. Now, to understand what has been and could potentially be done in the future to modify CCN activation in a model like CESM, let's just quickly try to understand some of the basics of the process. Now, there is something called this adiabatic cloud parcel theory, which is essentially just a zero-dimensional idealized framework that simulates CCN activation under given ambient conditions. Basically, we have these CCN inside an air parcel, and as this air parcel adiabatically rises along the atmospheric column, the temperature and pressure decreases while the supersaturation increases, resulting in the formation of droplets and therefore clouds. Now, this process depends on several aerosol properties as well as ambient conditions. However, due to certain computational limitations associated with the cloud parcel theory intrinsically, it cannot directly be implemented in a climate model framework because of the scale mismatch. It basically involves solving extremely complicated ordinary and partial differential equations analytically and so on and so forth. And so the CCN activation within climate models is parameterized. The current scheme in CESM, like a lot of other climate models, is Abdul Razak and Ghan 2000, otherwise known as ARG 2000. And it has many advantages, such as it's easy to implement, it's computationally cheap, it's very well studied and very well calibrated and tuned within most of the model frameworks. However, it has some shortcomings as well, such as it's a little bit too simplistic. It ignores kinetic limitations associated with CCN activation and droplet growth, and it tends to perform not very well when the aerosol concentrations are very large, such as those in polluted conditions. And these shortcomings can essentially introduce uncertainties in the estimation of cloud properties. Now, how do we improve all this? So, how I understand, there can be two possible approaches associated with that. First is by refactoring the existing ARG 2000. And second is by introducing more physical processes into the existing CCN activation, or by just completely, stripping apart ARG and introducing something completely new into the model. Now, before doing any of that, just to give an idea of what CCN concentrations in low-level clouds at, let's say, 0.1% ambient supersaturation would look like when ARG 2000 is active in CESM2. So the global mean comes out to be approximately 72 per cc in the vertical column between 850 millibars to 960 millibars approximately, which can be considered as like a physically plausible number. Now, CCN concentrations don't particularly tell much about the cloud effects associated with changing the CCN activation mechanism, but these quantities can still be a good sanity check for the implementation of any activation scheme within a climate model framework. And so, before going ahead, I'll just quickly give out some details of the CCN of the CSM simulations that I've used in today's presentation. It's basically like everything corresponds to CSM 2.1. All the results that I'm going to be discussing, they correspond to 10-year averages. The resolution for the model runs is 0.9 degrees by 1.25 degrees. And it's like all of the runs are basically atmosphere only runs with fixed SSTs and present aerosol emissions, unless otherwise specified. All right, so starting with approach number 1. Now, intrinsically within ARG, there is a lot of math involved, but the only important thing to note here are these two empirical parameters that come into the estimation of the ambient supersaturation that result in the activation of CCN. These two empirical parameters depend on the aerosol mode width, and their expression is consistent for all three of the aerosol modes that activate within the atmosphere. Now, a recent paper was published this year by Pratapaditya Ghosh in 2025 itself, where they suggested that these formulations, particularly for F and G, can be modified specifically for the accumulation mode aerosols. Moreover, they also introduced this third parameter called P, which looks something like this, and is also a function of the accumulation mode width to explicitly account for the kinetic limitations associated with the accumulation mode aerosols. And as for the results, they stay more or less similar to the baseline CESM with unchanged or the default ARG 2000 scheme, with the CCN concentrations averaging at about 72 per cc still. The second approach involves replacing ARG with new schemes, essentially by adding more physics in addition to the existing physics of ARG. And the first step in this approach involves incorporating a concept called population splitting, into CCN activation. This concept was first given by Funtukis and Ennis in 2005, specifically to apply for log normal aerosol modes. And simply put, we basically split the entire aerosol population into two parts. First, aerosols with sizes close to their activation diameters, which activate and grow rapidly. And second, aerosols with sizes much smaller than their activation diameters, which either remain unactivated or activate and grow slowly. And when we implement this new scheme, which I'm going to be referring to as FN05, the CCN concentrations look something like this and average at about 76 per cc in the same low cloud regime. The second step within the same approach involves explicit treatment of giant CCN, basically the coarse mode particles that are typically larger than about 1 micron in size and grow significantly faster than the so-called regular aerosol population. This scheme was originally built upon FN05 and was given by Barahona et al. 2010, and I'm going to be referring to this as B10 here on out. The CCN concentrations of B10 remain, again, fairly unchanged compared to the previous cases, and still averaging at about 76 per cc. And last but not the least, the third step in this approach involves the modification of aerosol hygroscopicity. The original framework called the Hybrid Activity Model, or HAM for short, is from my own 2022 paper. And to be fair, it looks kind of confusing. The main point here is that this hygroscopicity basically depends on the dry diameter of the aerosol particles. And by fitting this long expression to lots and lots of laboratory and field CCN activation datasets, I was basically able to simplify the whole thing into this nice little power law expression, which was then implemented in this work with both FN05 and B10. And both of these configurations were then referred to as FN05 kappa ham and B10 kappa ham. Again, with the implementation of these two schemes, the CCN concentrations, they still don't really change too much. They actually slightly decrease compared to the previous cases, but nothing major happens. In summary, the average low cloud CCN concentrations at 0.1% ambient supersaturation sort of vary between 64 per cc and 76 per cc. And to reiterate, these concentrations do not really say much about the differences in the activation schemes and how they sort of affect the climate and so on and so forth. And so for that, we basically need to take a deeper look into how the actual clouds may or may not be changing by changing the activation schemes. And for this presentation, I've included results corresponding to only FN05 kappa ham and B10 kappa ham, which were the two most comprehensive sets of modifications made to the activation scheme. Now, first, let us take a look at how the cloud droplets number changes relative to the baseline CESM configuration. Here, I've shown a comparison of the simulated CDNC, or cloud drop number concentration, with the MCD06 observations, which is just a modest product. The observations here are shown on the top left of the panel plot, also marked as OBS on the top left. And again, just like the CCN concentrations, the CDNC concentrations were also averaged in the low cloud region between 850 and 960 millibars. And there are three main things to note here about the agreements between the simulated CDNC and observed CDNC. First is that over the northern mid-latitudes, the estimates are a little bit unreliable due to these large patches of CDNC hotspots close to the polluted regions in the Southeast Asian and North American regions. Second, the estimate over the southern mid-latitudes improve due to the increased activation over the pristine Southern Ocean. And this is extremely promising because this region is potentially going to be important for marine cloud brightening experiments. And lastly, the estimates over the tropics, which is basically the region between -30° south and 30° north, they are kind of regionally poor. So we see these severe under predictions over the Pacific, and then large over predictions in the CDNC values over the Atlantic, which kind of brings the mean values close to the observations as well as reducing the RMSE, but they don't really represent the observations too well. And this is likely due to the existing issues within the deep convection scheme in CESM as well. Moving ahead, this is the comparison for the radiative forcing. This set of plots correspond to the short wave cloud forcing component. And like the previous slide, the panel on the top left are the observations from series EBAF products. The remaining three plots here are the differences between the simulated shortwave cloud forcing and the observations from series. Now, despite the biases, what we found was that the agreement was overall pretty good as far as the baseline CESM estimates was concerned with respect to the observations. The biases, not the biases, but the root mean square error between the observation and the simulation is shown on the left-hand side of each of the panels, with the value coming out to be approximately 8.5 for baseline CESM. And modifying the CCN activation essentially resulted in increased biases alongside increasing the root mean square error as well, mainly because of the forcing becoming stronger in both of these cases with respect to the observations. Now, this at least physically makes some sense because we have more droplets, we end up having more persistent and brighter clouds, thereby making the shortwave cloud forcing a lot stronger as compared to what we actually observe in reality. For the long wave component of the cloud forcing, we did not really see any changes with modifying the CCN activation. Now, this also makes sense as the long wave component is more strongly tied to mixed and ice phase cloud processes. And in the current stage of this work, we haven't really made too many changes within the ice phase processes anyway. So the long wave remained intact. All right, so far so good with the choices of the modified CCN activation in the model. mainly because there seems to be some sensible increase in the CDNCs. The downside as of now, on the other hand, is that the clouds have become excessively bright. Now, in order to tweak that, the idea was to sort of modify the droplet removal from clouds without making any explicit further changes to the droplet formation mechanism itself. And for that, I basically ran a bunch of sensitivity experiments related to these enlisted processes. Here I've shown what the results looked like when the baseline ARG activation scheme was still active in CESM. Also, we can think of these experiments to further fall under sort of three different categories. The first category is the modification to the aerosol emissions. Second is kind of like a miscellaneous set of modifications, which include secondary ice processes and subgrid turbulence. And third is the modification to the warm rain processes. I will further narrow down the discussion to focus on just these four sets of experiments, which seem to modify our original results most significantly. All right. First, let's take a look at how the CDNC changes. So the metrics on the top left of the plot corresponds to the baseline CESM relative to the observations. And the table summarizes the metrics for the modified CCN activation scheme. I've also boldened all of the best performance metrics corresponding to each of the activation scheme. For FN05 kappa ham, the base simulation without any further tweaks to any of the rain processes seems to stand out with the best performance metrics. However, using this scheme without any further changes might not be very sensible due to the resulting biases in the shortwave cloud forcing, as we saw a few minutes ago. For the B10 kappa ham case, the auto AG configuration marginally improves the model estimates. The auto AG configuration being the modifications to the auto conversion and accretion processes, while also implementing limiters on the cloud drop mass mixing ratio, and the rain mixing ratio. Now, for the shortwave cloud forcing, the results look very similar for both the modified CCN activation schemes. We see that the results for the auto ACK no limb configuration this time drastically improves the model estimates compared to other cases, as well as to the baseline CESM. The auto ACK no limb configuration basically produces almost a twofold improvement in the estimates for both CDNC as well as shortwave cloud forcing compared to the baseline CESM. And so we basically decided to use it for further assessment of the model. And for that, we first looked at the effects of the anthropogenic emissions on the shortwave cloud forcing. The PD and PI correspond to present-day and pre-industrial aerosol emissions, respectively, where the PD shortwave forcing is stronger than the pre-industrial forcing for each of the case due to increased aerosols in the present-day scenario, basically resulting in a net negative anthropogenic forcing for all three of the cases. The forcing in FN05 kappa ham is about 25% stronger compared to that in the baseline CESM, especially over the northern hemisphere around the regions in Southeast Asia as well as North America, as you can see from here. These are the regions which basically dominate the anthropogenic emissions in the atmosphere. The forcing in B10 kappa ham is stronger than baseline CESM, just like the previous case, but it's weaker than the FN05 kappa ham, particularly because of there being these small hotspots here and there where the PD minus PI shortwave cloud forcing happens to be positive. In addition to that, the negative cloud forcing is also not as strong as compared to what we actually observe in the FN05 kappa ham case. Next, we also looked at the residual at the top of the atmosphere or at the top of the model. Now, this quantity is also known as restom, which is basically just the difference between the net shortwave and long-wave flux at the top of the atmosphere. And the PD minus PI value basically captures how much additional energy is retained or lost within the climate system. The negative values that we see over here, they basically reflect like a dominant cooling effect in the model due to these anthropogenic aerosols, particularly from their interactions with the clouds. The way we interpret the PD minus PI restom is such that the more it deviates from zero, the more sensitive the climate can be classified to the anthropogenic changes. And the absolute value of PD minus PI in these simulations with the modified CCN activation schemes is larger than the baseline CESM, which basically just means that the climate happens to be more sensitive to the anthropogenic changes in both of these cases. And so we are going to be using these FN05 kappa ham as well as B10 kappa ham for further assessment of the climate. And I do have some preliminary results for the MCB experiments as well. But I think in the interest of time, I might just go over to the summary. And in case someone is interested in talking about the MCB results, I'd be happy to discuss those more in detail. But the first part of basically the first conclusive finding of this work so far is that the existing CCN activation can be essentially improved by adding more physics to the existing ARG 2000 scheme. The second main conclusion would be that fine-tuning of the model with the modified CCN activation schemes, be it FN05 or B10, can be used for correctly representing the climatology within CESM, and thereafter the same procedure having a lot of potential for representing the aerosol cloud interactions in general within other climate model frameworks as well. And last but not the least, the climate as well as the MCB assessments related to these modified CCN activation schemes is currently ongoing. And with that, thanks for listening. Any questions, comments, feedback?
Thank you very much. That was really cool. If anyone has questions, please put your hand up, or you can put them in the chat as well. I actually had a question about IMO because it looks like the shortwave cloud forcing in your modified activation scheme was quite a lot higher over the Northern Hemisphere oceans. Did you look at the effect of IMO, because I think your present day is like 2000s. So did you look at whether changing the shipping emissions in your modified activation scheme configuration reduced the forcing over the Northern Hemisphere oceans?
So I have not done that, but that's a good suggestion. Having the present day emissions set to like a much closer year or a much closer date to the actual present day, that might be useful changing some of these numbers, and might give it a lot more credit as compared to what we see over here. The other thing would be that all of these simulations, like none of these simulations are matched. So that might also be like a contributory factor to what we see as far as the anthropogenic forcing is actually concerned.
Cool. Yeah, I think that's a question a lot of people are worried about. So it'd be cool to see those results. Yeah. Does anyone else have a question? If not, we can move on to Jake. If you have any further questions, please put them in the chat. I'm sure Kanishk will be happy to respond to them. But thank you, Kanishk. If you don't mind, yeah, thank you. And so our second speaker today is Jake Gristey from NOAA, and Jake will be talking about changes in cloud brightness caused by stratospheric aerosol injection. So Jake, please go ahead.
Yeah, just make sure I unmute. There we go. Do you see the screen now?
Yep, all good. Go ahead.
Yeah, so thanks for the introduction and for the opportunity to share with you all some of the work that I've been doing together with Graham Feingold from NOAA, looking at changes in cloud brightness caused by stratospheric aerosol injection. Yeah, so I wanted to start with this schematic here, which is a sort of a visual representation of the concept that I would like to present today. So what you're looking at is a cloudy scene over the ocean. The yellow arrows at the top of the slide here are indicating the incoming solar radiation at the top of the atmosphere. And then sort of superimposed on this are two of the most well-studied approaches to solar radiation management. And I should clarify that I'm not interested in advocating for the implementation of these approaches. My interest here is really in understanding the processes that would be operating if these approaches were implemented. So in the lower left here, I'm showing marine cloud brightening, or MCB, and this would involve the release of aerosol particles into these low-level clouds, which can cause the liquid water in the clouds to be distributed over a larger number of smaller droplets. So you can compare this cloud on the left to the cloud in the middle here. This is my sort of unperturbed cloud. This can increase the cloud albedo. So this is the so-called Toomey effect. And then this can also have knock-on effects on the cloud lifetime. So these smaller droplets might evaporate more quickly, but they also might lead to slower precipitation and a rain out of these clouds. And these cloud lifetime effects introduce a lot of uncertainty into the marine cloud brightening problem. What I wanted to show here is that in addition to brightening the clouds microphysically, it's also possible to brighten the clouds by changing the angle at which the solar radiation is entering the clouds from above. On the right here, you see the stratospheric aerosol injection approach. The general idea here is that aerosols would be released into the upper atmosphere, into the stratosphere. The primary intention is to reflect some of this incoming solar radiation back to space. This is the aerosol reflection arrow that I'm showing in the upper right. But one of the known sort of side effects of SAI is that this can cause a diffusion of the radiation field. So as well as reflecting some of the incoming sunlight back to space, the radiation can be scattered into different directions downwards. So this diffuses the radiation field. This can change the average angle at which the solar radiation is entering the clouds below. And this in turn can change the cloud albedo. So we call this effect diffusion brightening. And this can occur even for the same cloud properties. So again, compared to the unperturbed cloud in the middle here. So previous studies have looked at the impact of this diffusion of the radiation field on, for example, agriculture and renewable energy applications. But as far as we were aware, this diffusion brightening effect of the clouds had not been previously quantified. So what I'll show here are some radiative transfer calculations that try to quantify this effect. But the first question that you might ask here is, why does the cloud albedo depend on the angle at which the solar radiation is entering the clouds? And it turns out that this has a fairly straightforward explanation. So what I'm showing on this slide here is just a cloud layer going across the middle of the slide. And I am showing a solar photon that's entering the cloud from directly overhead. So I'll call this an incidence angle of 0 degrees. This photon will travel some distance into the cloud before interacting with a cloud droplet. And for solar radiation interacting with cloud droplets, it's almost certain that this photon will be scattered. And the direction that it's scattered into is determined by what's called the phase function. So in this example here, I'm just going to say that the photon has been scattered into this direction, but the probability of being scattered into any given direction is shown by this sort of thin black line here. And the key point is that it's far more likely that this photon is scattered into the forward direction, was have this narrow forward scattering peak. And again, the photon, after being scattered, would travel some distance until interacting with the next cloud droplet, and this multiple scattering process ensues until the photon leaves the base of the cloud. And sort of the key point here is that because of this preference for forward scattering, a photon entering from directly overhead is more likely to penetrate deeper into the cloud and escape the cloud base compared with a photon that's entering at a steeper angle. So what I'm showing on the right here, this is actually the same photon trajectory. I've just rotated it over by 60 degrees. You now see that this first scattering event, the preference for forward scattering now has a lateral component. And after exactly the same series of scattering events, that photon is still within the cloud. And it may be the case that it's scattered downwards, but The point here is that statistically it has another opportunity to be scattered back out the top of the cloud, and therefore the cloud albedo increases when it's illuminated from steeper angles. And this can easily be shown with a Monte Carlo radiative transfer code. I don't have time to show that today, but I have that in the backup slides if anybody is interested to see that. So bringing this back to the SAI problem, we set up an idealized radiative transfer code to try to understand how the diffusion of the radiation field from SAI might change the angle at which the radiation is entering the clouds below, and therefore the cloud albedo. So what you're looking at on the left here is the vertical profile of temperature from the US 62 standard atmosphere. This standard atmosphere also has vertical profiles of all of the radiatively active trace gases, which are included in these calculations, although I'm not showing them on this plot here. For the radiative transfer model, we include an ocean surface with a Lambertian reflection. So this just means that the radiation is reflected evenly in all directions from the surface. We add a cloud layer from 1 to 2 kilometers. This is a liquid cloud with a cloud optical depth of 10, an effective radius of 8 microns. These are sort of typical properties of these marine stratocumulus clouds, although I'll show the sensitivity to this cloud optical depth, the COD, later. To emulate the stratospheric aerosol injection scenario, I added an aerosol layer from 20 to 21 kilometers. I set the aerosol model to be fresh volcanic, which is a model that's built into this radiative transfer code, and this represents the optical properties of the aerosol, so it relates to things like the size distribution and the composition of the aerosol. And I chose this model because stratovolcanic eruptions are often sort of used as a proxy for SAI. And then the aerosol optical depth I set to a value of 1. So this is a fairly heavy aerosol loading, but the idea here was to initially really diffuse the radiation field and see if we can see some effect here. But I'll test the sensitivity to this later. And then finally, the solar geometry, I set the solar zenith angle to 0 degrees, so that's a sort of an overhead sun. But again, I'll show the sensitivity to this. And then other important settings in SB-DART is the radiative transfer code that I use for these calculations. I calculated the solar radiation from 0.2 to 5 microns every 5 nanometers, and then spectrally integrated to get the broadband solar energy. And then I ran these calculations with 20 streams. So in a radiation code that you might find in a climate model, it's typically 2 streams. So at each layer of the atmosphere, the radiation is calculated in the upward direction and the downward direction. But with 20 streams, we're tracking the radiation that's traveling in 20 discrete different directions at each atmospheric layer. And this enables us to resolve the angular distribution of the radiation field very well, which we suspected would be important for this problem that involves diffusion of the radiation field and spreading the radiation into different angles. Okay, so onto some results now. This plot on the left is showing the simulation results without the stratospheric aerosol. So the same as the setup that I just showed, but without the stratospheric aerosol layer. And what you're looking at is the downward solar radiation flux. In blue, the direct component, and then in orange, the diffuse component. So the way to sort of read this plot is starting at the top here at 30 kilometers. The radiation, the downward solar radiation is almost entirely in the direct solar beam. And that continues to be the case all the way down to the cloud layer. So recall the cloud is at 1 to 2 kilometers. And then the cloud extinguishes the direct beam and introduces some diffuse radiation. There's a very small amount of diffuse radiation above the cloud that's associated with molecular scattering. But the key point here is that the radiation that's coming into the top of the cloud is almost entirely in the direct solar beam. This plot on the right here is the same, but with the stratospheric aerosol layer included. And you see that the story is very different. So the radiation is in the direct beam down to the aerosol layer, which again was at 20 to 21 kilometers. But you see that the aerosol layer depletes the direct beam, and much of that radiation is scattered forwards and then resides in the diffuse radiation. So coming all the way down to the cloud layer, you now see that most of the radiation that's entering the cloud top is in the diffuse radiation rather than the direct beam. Okay, so how does this change the cloud albedo? Apologies, I'm using the same colors here, but these are now different quantities. So the blue is now the total downward solar radiation flux at each level, and then the orange is the total upward solar radiation flux. And if we just go to 2 kilometers to the cloud top and take the upwelling solar radiation flux divided by the downwelling solar radiation flux, that's the definition of the cloud albedo, we get a value of 0.415. So this is telling us that of all of the solar radiation that's entering the top of the cloud, 41.5% of it is being reflected back upwards. So that's the case without the stratospheric aerosol. For the simulation with the stratospheric aerosol, if we do that same calculation at the cloud top, take the ratio of the upward to the downward solar radiation flux, that number comes out as 0.454. And so comparing these 2 numbers, what we find, and this is sort of the key point on this slide here, is that there's almost a 10% increase in the low cloud albedo in this idealized SAI scenario. And just to emphasize, the only thing that's changing between these 2 calculations is I've just added this aerosol layer, which is diffusing the radiation field, changing the angle at which the radiation is entering the cloud below. And this is increasing the cloud albedo by almost 10%. So we also recognize that this is a very idealized setup. So the next thing we want to do is to come back and see how this cloud albedo enhancement depends on some of the assumptions that we made in the radiative transfer, particularly how we defined the cloud layer, the aerosol layer, and the solar geometry. Just coming to this plot on the right-hand side here, this just shows the red box is showing that I've run a set of additional calculations, but I varied the stratospheric aerosol optical depth from a sort of a light aerosol loading to a heavy aerosol loading. So that's what's shown on the horizontal axis here, the stratospheric aerosol optical depth. And then on the vertical axis is this cloud albedo enhancement. And the star value here is showing the default calculation. So almost a 10% enhancement for stratospheric aerosol optical depth of 1. You see a positive relationship here, which makes sense. The more stratospheric aerosols, more diffusion of the radiation field, more brightening of the clouds below. And we also see that this relationship is close to linear. So if the actual stratospheric aerosol optical depth was, say, 0.5, then you can read off that the cloud albedo enhancement would be 5 to 6%. If it was down at 0.1, then it might be closer to 1 or 2%. And the next set of calculations that I varied is the cloud optical depth. So again, shown in the red box in the lower right here. I ran some simulations from a very optically thin, sort of semi-transparent cloud to an optically thick, sort of juicy cloud. So that's the horizontal axis. Here is the cloud optical depth, and then the vertical axis again, the cloud albedo enhancement. The star here is again the close to 10% enhancement at the default cloud optical depth of 10. You see that this enhancement is larger at smaller cloud optical depths, and the enhancement is smaller at larger cloud optical depths. And again, this sort of makes sense. If at these very large cloud optical depths, the cloud is already very bright, so it's going to turn those photons around and reflect the radiation back upwards, regardless of the angle at which the solar radiation is entering. So there's not as much sort of relative enhancement. And then finally, again, the red box on the right here is showing that I ran some additional calculations, but varied the solar geometry. So from a solar zenith angle of 0 directly overhead to a sun closer to the horizon. So again, that's on the horizontal axis here. And this time you see that the sort of default cloud albedo enhancement of close to 10% was a maximum value, and as the sun becomes lower in the sky, this enhancement decreases, and it can actually turn negative. And again, this makes sense that if the sun is already very low in the sky, then the solar radiation would be entering the cloud at a steep angle without the stratospheric aerosol layer. So by diffusing the radiation field, this can actually turn photons back around to closer to overhead. But it's sort of important to recognize on this plot here that the solar energy that's input to the Earth system is disproportionately larger at these smaller solar zenith angles. So the solar energy itself scales as the cosine of the solar zenith angle. So these larger cloud albedo enhancements would have a disproportionately larger contribution towards the total solar energy. And then something that you saw in all of these plots is this dashed orange line as well as the blue line. So this was just showing that the general behavior across all of these different cases was captured with even a two-stream radiation code. So this was an interesting result to us and maybe has implications for how this effect might already be captured in existing models. So we looked at the sensitivity to these various different properties, and then the last result that I wanted to show here is that it is asking the question of, okay, we have this inadvertent brightening of the clouds below. How much does this contribute to the overall top of atmosphere radiative effect of a stratospheric aerosol injection? So that's what's shown on the vertical axis here. This is the top of atmosphere radiative effect of the stratospheric aerosol injection. And I'm plotting this as a function of the cloud optical depth. So the green line is showing the total radiative effect, which decreases towards larger cloud optical depths, which again makes sense if there is already a very bright cloud in the scene. Then if you add a stratospheric aerosol layer, that doesn't do much to add additional brightness to the scene. But with the radiative transfer code, we can break this total contribution down into the reflection directly from the stratospheric aerosol layer, which is in the blue dashed line, and then this inadvertent brightening of the clouds below, this diffusion brightening effect, which I'm showing in the orange dotted line. And so there's a couple of interesting features to point out here. First of all, the stratospheric aerosol reflection dominates at small cloud optical depths, which makes sense. If there's very little clouds there in the first place, then you don't get much cloud albedo enhancement. But this reverses at a cloud optical depth of about 4. So beyond the cloud optical depth of 4, this diffusion brightening effect of the clouds below actually dominates the radiative effect at the top of the atmosphere over the reflection from the aerosol layer itself. And beyond cloud optical depths of about 17, you see that the stratospheric aerosol reflection turns negative, which is interesting. And this occurs even for conservative scattering aerosols. So I should have mentioned that these calculations were done with an aerosol single scattering albedo of 1. So this is sort of an ideal case for an aerosol composition of SAI, fully scattering aerosol. But this can still lead to a negative radiative effect or a warming of the scene. And this is associated with the fact that the aerosols can become more effective at trapping radiation below the aerosol layer than reflecting radiation back to space if the surface below is very bright. I can say more about that if there is interest. And then out of these larger cloud optical depths, this diffusion brightening effect really dominates the total, and it's the only reason that the stratospheric aerosol injection continues to cool the scene, have a cooling effect, is this inadvertent brightening of the clouds below. So trying to relate this back to the types of clouds that actually occur in reality, if we look at the frequency of daytime clouds, about 20% of clouds occur in this regime between 0 to 3 cloud optical depth. But the remaining 80% occur at cloud optical depths above 3, where this diffusion brightening effect of the clouds below really dominates the overall radiative effect. And also keep in mind that clouds themselves cover about 60 to 70% of the Earth at any given time. So the types of conditions where this diffusion brightening effect would dominate are likely to be quite common on Earth. And I don't think this has necessarily been fully appreciated in previous assessments of SAI. Okay, so to summarize here, I showed that the cloud albedo increases at steeper illumination angles. This sort of emerges from fundamental physics and geometry arguments. In an SAI scenario where we would have diffusion of the radiation field by stratospheric aerosol, the cloud albedo can be enhanced by about 10%, but this number here really depends strongly on the aerosol cloud and sun conditions that are present or that were assumed in the calculations. And then thinking about the overall contribution that this has to a SAI scenario, that this diffusion brightening effect would dominate the overall radiative effect of SAI in conditions that occur at many locations and times on Earth. And so these are results that we published earlier this year in a GRL paper. And for a quicker digest, there are a couple of news articles that came out on this as well. So I'll stop there and see if there are any questions.
Thank you, Jake. Any questions from the audience? If not, I have a question. So the bottom plot here, would it be similar if the total AOD was like 0.1, which is sort of more in line with sort of realistic scenarios, right? You wouldn't.
Yeah, so I've been asked this question before. So,
Okay.
So yeah, I produced this. So these are the results reproduced for an AOD of 0.1. So this is the plot that I think you were asking about on the right. Yeah. So the axes are a bit reverse, so negative is what I was previously showing as positive. But the answer is yes, that the general behavior is reproduced for aerosol optical depth of say 0.1 as a global mean. If you look at the scales on the vertical axis, it's about a factor of 10. So like I was showing earlier, this relationship between the cloud albedo enhancement and the stratospheric aerosol optical depth is fairly linear. And if I jump back to the plot that I was showing here, if you look at the scales, it's sort of minus 20 to 100, whereas for AOD of 0.1, we're looking at about a factor of 10 decrease in that scale for a factor of 10 decrease in the AOD. But the general behavior and this result of the diffusion brightening dominating the overall radiative effect would hold at a smaller AOD as well.
Cool. Yeah. And can you say again why the stratospheric aerosol reflection contribution goes negative for the dark cloud? Oh, sorry, a cloud with large optical depth.
Right. So this contribution here, yeah. So this was a bit counterintuitive, and when I first saw this, it took me a while to work this out, and I actually came back to a paper from Jim Hayward in the 90s, which basically showed that if you have an overhead sun and a very bright surface below, or equivalently very bright clouds below the aerosol layer, then what happens is the radiation, when it's traveling on the way down, it has a very short path through the aerosol layer. So a lot of the radiation is able to travel through the aerosol layer, and not as much as reflected back upwards. But after that radiation is then scattered by the clouds below and travels back upwards, it's now that radiation has been diffused, it's traveling in all directions. So the radiation on the way back up has a longer path length through that aerosol layer than it had on the way down. So there's more chance of the aerosol layer actually scattering that upwelling radiation back downwards again. And if the surface below is very bright, then this sort of trapping of the radiation below the aerosol layer can exceed the reflection of the incoming radiation that's initially reflected upwards by the aerosol layer. So that's an interesting result.
Yeah. Very nice. Cool. Yeah, that makes a lot of sense. Anyone else have questions? If not, I think we can wrap up. Oh, no, Sarah has a question. Go ahead, Sarah.
Yeah, so sorry, Jake, having just walked through that description, this I assume is for overhead sun for zenith angle. So does that crossover point where the stratospheric aerosol becomes, having the opposite effect of what you want, change with solar zenith angle? I would think it would.
Yeah, good question. So you're asking about this point here. Hopefully you can still see my mouse where the at the cloud optical depth of about 4, where these two cross over.
Well, and also the crossover to that one right there. Yeah.
Yeah. So this crossover here, I'm confident to say that that for a lower sun angle, this would not go below 0. This would stay above 0. So this is a feature that sort of only occurs when you have close to an overhead sun.
Okay.
Yeah, the other crossover between the reflection from the aerosol layer and the brightening of the clouds, that one, I think I would have to run the calculations to check. It's not immediately obvious to me how this would shift with different solar zenith angles. So, yeah.
Thank you.
Cool. I think we'll wrap up here. Thank you very much, Jake and Kanishk. And if anyone else wants to give a talk about your science, please get in touch. And yeah, we'll wrap up here. Thank you very much, everyone.